There is a current carrying conductor. As we know, if there is a current carrying conductor, it produces magnetic field around it. We need to understand how is that magnetic field distributed. What pattern of magnetic lines of force around the conductor? This geometry we have drawn gives us the information about the magnetic lines of force around the conductor. There is a straight conductor, electric conductor carrying current, straight line, and these are concentric circles, that is closed circular paths. These concentric circles are drawn about a single point. There is a concentric circle about this point. Shows magnetic lines of force. These concentric circles, in the same fashion, can arise at different points on the conductor. At this point, you have one more set of these concentric circles. At this point, one more set. At this point, one more set. So we have concentric circles at every point all around. These concentric circles means magnetic lines of force, which is closer. Circle is closer to this point, closer to this line. This line is passing through the center, and these lines, so this circle, concentric lines are perpendicular to this straight line, showing that magnetic field decreases as you move away from this. This line has more force, and this line has less magnetic force. This line has even less magnetic force. These are the concentric. This is how the electric field are distributed in terms of magnetic lines of force. If that is the case, what would be the direction of these magnetic lines of force? Here the direction is given in the anti-clockwise direction, because that the circle is anti-clockwise direction. Direction shows that. To indicate the direction of the magnetic lines, there are rules. The rule is framed. That is, one rule is in physics. It is called right hand palm rule. What is meant by right hand palm rule? Using this, one can give the direction of the what is our magnetic lines of force around the conductor. What does it say? This is the one I say is a conductor carrying current, direction of the current. Palm means right hand. You have to hold the conductor in the right hand with a palm like this. The thumb showing the direction of the current, and these fingers encircling the conductor showing the direction of the magnetic field, direction of the magnetic lines of force. These are the concentric circles. Of course, concentric circle about different points. The same thing I have done. Anti-clockwise direction. These fingers remaining fingers will show the direction of magnetic lines of force around the conductor. This finger shows the direction of the current in the conductor. The same conductor, if it reverses the direction of the current like this, the same rule can be applied here also. That is a direction like this. But you hold it not like this. Hold the conductor with a palm like this, so that the thumb is directing towards the current. And these fingers, what is that? These fingers will indicate direction of magnetic lines of force around the conductor. That is encircling. The same thing I have done. These fingers show that clockwise direction. So this is about what is the direction of the magnetic lines of force about the conductor carrying current in two different directions. It is assigned using right hand palm rule. The same rule can be applied to find the direction of the current at any point in the space. The space means the space in which there is a conductor carrying current. This is a space like this. Just to understand this, I am taking one circle, that is concentric circle about this point. I want to indicate what is the direction of the magnetic field at this point. The point is on the line. What is the direction? As you know, direction of the magnetic field at any point on the circle is represented by drawing a tangent to the curve, tangent to the circle at that point. If you do so, tangent means this circle is perpendicular to the line. If you draw a tangent to this point like this, it is always a perpendicular line. This perpendicular to the plane where the point and the line are written. That is a tangent perpendicular to the plane at this point. That is direction of the magnetic field in the perpendicular direction, either inward or outward. It is decided by the palm rule. The same rule. Like that. Hold this conductor like this, palm. The point is here. And move the fingers. This is direction of current. Move the finger. The fingers are moving what is that inward direction. That is, field is always perpendicular, magnetic field. Inward means that is the point at which direction is inward, going in to the plane. This point is perpendicular and inward. It is symbolized by a small circle inside a cross. It is inward. If the point is on the left hand side, you can take any point on the right hand side, it's the same kind like this. If you have taken the point on the left hand side, follow the same rule. Left hand side means hold the conductor like this and move the finger like this. Here, move the fingers exactly, still it reaches the point like this. When the fingers reach the point, the fingers what is that moving, what is that outward, showing outward direction like this. That means the magnetic field is perpendicular to this point and perpendicular to the plane, but outward direction. There is a direction. The symbol is circle with a dot inside. These are the symbols used in physics. If any symbols like this on a plane of paper on either side of the conductor, that is tangent or magnetic field is inward, perpendicular inward, perpendicular outward, perpendicular to this line and this point at the same plane. That is a significance of this palm rule. What I have taken the direction of the current in the opposite direction, the same. Here current, that is a magnetic line's direction also changes like this. Using this, that is inward or outward, we can understand. That is holding this direction like this you have to hold it. So hold the conductor like this, showing the direction, finger, thumb showing the direction of the current, and these fingers, the point is here, and move the fingers like this. Fingers move inward. This side, the point is inward direction. What about here? And encircle the conductor and move the fingers like this till the point is reached, layer outward. Finally, the finger showing outward direction. This point is outward. That is, magnetic field is perpendicular and outward. Perpendicular, inward. If the direction of the current is this. This you need to understand, very important. Right hand palm rule gives the direction of the magnetic lines of force and also direction of magnetic field at any point in the space around the conductor. This is about the direction, magnetic field direction. Now, what is the magnitude of that field that we need to understand? There is a conductor carrying current in the space. How do we estimate? That is the amount of magnetic field at that point. Estimation, or how do you calculate amount of magnetic field at any point in the space? That is given by a mathematical law or mathematical statement in the physics. That mathematical law is Biot-Savart's law. What does it say? It is said in both, what is that? It explains both vector direction as well as the magnitude of the field. Vector direction of the field as well as magnitude of the field. Here given the mathematical formula of the law, mathematical statement of the law. It is based on this diagram. It is Biot-Savart's law. Here the same, what is that? A conductor carrying current of some length L, finite length, current is I, and around the point, I am taking the point in the space somewhere here, that is a point B. We need to estimate what is the amount of magnetic field at this point. Draw a straight line from here to this point. At this point, I am considering the length as dl, that is the element, infinitesimally small length, element of length. Finite length is L. At this point, dl is the infinitesimal value. This dl is a vector because L is a vector in the direction of I, but I is not a vector. So dl value, this small length is a vector, this r is a vector. What is that? Position vector. Distance between this point and this point is a vector. And these two vectors are, what is that? Are separated by angle theta. That is angle between these two vectors. About this diagram, what amount of magnetic field this element produces at this point due to this conductor? This is the one is given. That is dB, you should write. This is dB. Plus I get dl. dB dB. So element is infinitesimal value. The amount is what is the infinitesimal value? dB. Magnitude is directly proportional to I into the product of vector product of these two. These two are vector. Vector product of these two divided by R cube. Depends on the current strength as well as magnitude of dl, magnitude of R. That's a mathematical statement, is a vector form of the law. Savard's law. Magnetic field at this point. If you want, what is that? Only scalar form, only magnitude of this value, you write the what is that formula for this? What is the formula? Formula for the cross product of two vectors. That is A cross B equals A into B sin theta. Vector product. Now it is written as a, we can replace this by R sin theta. So dl into R sin theta. Magnitude of that is dl R into sin theta. Now when R cancel, it is R square. Finally, what is our final expression? Only for the magnitude of the field, magnetic field at this point is mu naught by 4 pi I into dl sin theta by R square. It is proportionality constant, proportional to this function. Sin theta. What is theta? Angle between this vector and this vector, this line and this line. Here, scalar form. So dB is depending on the strength of the current and dl element taken and the angle theta. Angle theta is varying from 0 to 90 degree. If the line closer to this, it becomes 0. If the line perpendicular to this, becomes 90, varying from 0 to 90. If theta is 0, that is magnetic field is 0 on the magnetic field is 0 on any point on the conductor. If theta is 90 perpendicular, magnetic field is maximum with this angle. That is scalar form of Savard's law. Mu naught by 4 pi mu naught is magnetic permeability. It is a constant of proportionality. It is directly proportional to current strength into L and theta, inversely proportional to R, square of the distance. That is, as the point is more away from the conductor, the field strength decreases. Using this mathematical statement, we can go for derivations for B for different configurations of conductor. I am taking the configuration of the conductor is a straight line, very straight, no bend. And for a finite length. So here I have taken a finite length of the current carrying conductor. We are deriving magnetic field at a point due to finite straight current carrying wire. Finite means has some finite length L. I is current in the conductor. So for this one it requires some, what is that, geometry, that is geometrical drawings. Let me take a point here in the space around the conductor. You can take point anywhere like this. With this point, draw a perpendicular distance from this conductor, perpendicular line. Length is a perpendicular line. From this point, draw a straight line. What is the dotted straight line from here? Straight line from this point. From here to here, the length is L, definite or finite length. Now we can write this angle. Angle between this line and the vertical line is eta 1. Angle between this line and this line, vertical line and this line meeting at this is eta 2. This is a diagram. Let me take the element dl. Anywhere you can take either point here, any point or another. I will take the element dl at this point on the conductor. You have to write the expression for magnetic field at this point due to dl. That is, you have to draw the geometry from this point to this point, a straight line. With this straight line, angle is 90 degree. With this drawing, we get what is a right angle triangle in this geometry. Let us call this as angle as theta. If this angle is theta, what would be the angle between this? That is between this line is 90 minus theta, because already it is 90 degree. Now, what is the dB value due to this dl at this point using Biot-Savart's law? That is using the same formula. Use the formula dB equals mu naught by 4 pi. I means current in this conductor. dl sine of the angle. What is the angle? This angle, not this angle. Angle between this vector and this vector, 90 minus theta. Here theta will be 90 minus theta. And r square distance between these two. So in this diagram, right angle triangle, this value is known A, this value is R, this value is L. Distance between these 2 points is L. So this, in the right angle triangle, this side is known as adjacent side, and this side we can call it as opposite side. This is hypotenuse. This is a what is that? Mathematical. Let us go. This is a mathematical form of the law. Let us go for simplification of this equation. As you know, sin 90 minus theta is cos theta. Right side 90 minus theta is cos theta. That is a differential equation, differential form. I want integral form for finite values. Integrate the equation. Left hand side, right hand side. Integration of this, integration of this. These are constants. I is a constant. Assume I is constant in the conductor. Integration of this is the function. These are the functions. And here carries what is that, limits are there. For this length, total length, in terms of angle, that is variable, what is that? Angle is, for this variation of length, the angle is varying from here to here. That is eta 1, eta 2, eta 1. IR now, what is that? Line is 0. If you take this line as 0, we take these values of angle as negative values. We take these values of angle as positive value. That is why minus eta 2 plus eta 1. Angle variation. Not in terms of length variation. Here the angles are taken. The function we have theta is here. Here function dl is there, r is there. You have to find this function in terms of the angle theta. It is possible. For that one, look at this triangle. For this right angle triangle, we can write this as cos theta equals adjacent by hypotenuse a by r, and also tan theta equals opposite by adjacent l by a. With this formula gives r equals a by cos theta. So function r we can write in terms of a by cos in terms of theta. That is one you get. Second equation, you can call this as equation 1, equation 2. But tan theta equals l by a, you can rewrite this as l equals a tan theta. I want dl. For the dl, you have to differentiate this equation with respect to theta. dl by d theta is equals a is constant. Differentiation of tan theta with respect to theta is secant square theta. If that is so, what is dl? That is a secant square theta into d theta. Look at this equation. dl, you can write it as in terms of theta as a secant square theta d theta. Call it as equation number 3. So we have equation 2 and 3. We can put these two equations into one and see what we get. This is what we get. Integration of dl is a secant square theta into d theta. Written here oppose. Cos theta remains numerator. And r square, what is r? A by cos theta. R square is whole square, that is a square by cos square theta. You know 1 by cos square theta equals secant square theta. 1 by cos theta is secant theta. 1 by cos square theta is equal to secant square theta. That is 1 over cos theta is secant square theta. This secant square theta numerator and denominator get cancelled. 1a square is there and a is there. 1a get cancelled, 1a remains in the denominator and cos theta d theta will remain in the numerator. This remains same. Integration is not yet done. Then we go for integration of this. With all this function, you have taken all of them, all the functions in terms of theta, and here integration on the left hand side, finite value b. This is a constant. I have taken this a as a constant out of the integral sign. denominator I by a. And integration of cos theta with respect to theta is sin theta. Integration function. And the limits are there, apply the limits. Lower limit, upper limit. Write the function with upper limit minus the function with the lower limit. Sin of minus sin of. Upper limit minus lower limit is minus theta. As you know, sin of minus theta is minus sin theta. This becomes minus into minus plus sin pi to sin pi 1. This is the final equation. B is equal to, written here, B equals mu naught by 4 pi into I by a into sin pi plus sin pi 1 plus sin pi 2. So B is the, what is that, amount of magnetic field at this point due to this current carrying conductor having a finite length L. I divided by A. Theta 1, eta 1, eta 2 are measured, that is in the opposite direction. Here 0 from here opposite direction now. Take the positive value, here also positive value is opposite direction. This is the expression for the amount of magnetic field at a point in space. So we can extend this to some special cases, this equation. Here case 1, if you take the conductor of infinite length, that is infinite straight current carrying wire, what is the B at this point? What is infinite from this point? This point is what is moving towards infinite distance, and this end point is moving towards infinite distance downward direction. If the points are moving towards infinite distance, what would be the angle between this line and this line? Look at this. If the point is moving towards infinite and moving away, this angle increases like this. Increases. If it is reaching to infinite, almost becomes vertical. Same case is applicable. If the point is moving towards infinite distance, this line, what is that? Angle increases, almost becomes vertical to this point. This eta 1 angle is 90 degree, eta 2 angle is 90 degree, 90 degree. Put into this equation. Sin 90 plus sin 90, 1 plus sin 1 plus 1, and the equation becomes 2 here. B into mu naught by 4 pi into 2I by A. That is the amount of magnetic field at the point if the current carrying conductor has an infinite length. Is that mathematical equation? And if the current carrying conductor is semi-infinite, that is semi-infinite straight current carrying wire. What is meant by semi-infinite wire means here the point is midpoint, that is a straight line perpendicular this point, perpendicular distance. Only this point is moving towards infinite distance. Only this length is infinite. And this length, what is that? This point is approaching towards this point. That means semi-infinite. There is no length in this side. If this point is moving towards this, then this line is almost perpendicular. Same case like this. What about this line? In the semi, this point is approaching closer to this point. If the line, what is that now? Point is approaching, the angle, what is that? Here decreases, because when coinciding becomes 0. Eta 2 equals 0, eta 1 equals 90. This is 1, sin 0 is 0. So this is 0, this is 1, moral 1. So it becomes 1, mu naught I by 4 pi A. That is the magnitude of what is that field at this point due to semi-infinite straight carrying current. In that cases like this you can apply that. So this mathematical equation for a straight conductor of finite length. So this is how we can have different derivations. This is one derivation for this. So we shall continue with this in the next class. Thank you very much.